about tonight is just the concept, first of all, of number. I think that one of the difficulties that this rising generation is going to face, maybe not your children in particular, but this new generation, is that the digital equipment is so available, so fast, that the concept of number and the concept of numeral are going to get mixed up. And what I mean by that is we're going to have a generation which, when you say 42, is going to picture the 1, 2, 3, 4, 5, 6, 7, and they're going to picture 4, 2, like that. And they're not going to picture 42 sheep on the hillside or 42 trees or anything like that. And it's very, very difficult. Already among ourselves, we've discussed how some people are kinesthetic learners. And by kinesthetic learners, we mean what I experienced with my firstborn. When I showed him 4 plus 8 equals 12, he couldn't learn it. I spent a half an hour one time with 3 addition problems, which he was having difficulty with, and at the end of a half an hour, he still couldn't look at 4 plus 8 and tell me that it was 12. And I thought, okay, either I'm going to kill you, or we're not going to do flashcards anymore. So we elected not to do flashcards, but I really, even then, didn't understand. Here's the problem. Why should something that looks like a box and something that looks like a snowman be the same as something that looks like a snake and something that looks like a stick? What is that equation about? It doesn't make any sense. And furthermore, if I said to him there were 8 elephants and 4 elephants joined them, he knew perfectly well that there were 12 elephants. He had no problem at all. Even when it was just verbalized, I didn't have to draw pictures. But if I said that, he could get it. And if I held up the card, he could not get it. And it was just a revelation to me. But what I want to say to you is, that was a long time ago, and things are very much worse. The children are seeing numerals, which is not the same thing as a number, and they're seeing cute pictures, but number is really a very abstract idea. Now, in the 50s already, so 70 years ago almost, a fellow named Glenn Doman was working with brain-damaged children. And he said, it doesn't matter whether they're brain damaged because of a genetic problem or because somebody hit them with a hammer, it all comes out the same. You need to teach things very, very carefully. You need to understand the concepts one by one. And he did lots of clever stuff, just the way Maria Montessori did when she was dealing with disadvantaged children. But in the end, these mothers who had their damaged children competing with normal children had other children who were normal from the beginning. And here's what Glenn Doman found out. A normal child can learn not only to see something like, how many is this? 2. But he can look at something like this and say it's 19. And he can even look at something like this and say 43. And that is normal if it's presented the right way. And what he did, he has a book out called Teach Your Baby Math. And you start out with these cards, and you have a card with 1 dot on it, and you have a card with 2 dots, 3 dots, and so forth. And you show the cards from 1 to 10. 1, this is 1, this is 2, this is 3, up to 10, and then stop. And you can do it 2 or 3 times in a day, and the next day you start, this is 2, this is 3, up to 11. Now, what's important about the dots is that the only difference between these 2 cards is that this one has 2 dots and this one has 3. That's the only difference. And because it's the only difference, you actually are putting the concept of number before a child. If you have, 2 chicks and 3 turtles and 4 trucks, it's not really clear what's happening. And if you count like this, 1, 2, 3, 4, 5, here's the deal. This is 1 finger, this is 1 finger, this is 1 finger, this is 1 finger, and that's your thumb. So it's not really clear what you're saying. It's a little bit clearer if you say 1, 2, 3, 4, 5. That's better. But the dots are just perfectly clear. And furthermore, which you can't do on your fingers, you can go all the way up to 100. And so what he says is, that's the thing to do. And when you get up to about 20, so now when you get up to 20, you're saying, this is 11, this is 12. And then, in a sense, by way of review, but also because there's more interesting things to know, you hold up the card with 7 dots, and you say, 3 plus 4 equals 7. And you hold up the card with 9 dots, and you say, 3 plus 6 equals 9. And you hold up the 5 card, and you say, 2 plus 3 equals 5. That's all you say. Now you've introduced the concept plus, you've introduced the concept equals, you've introduced addition, and it's all perfectly clear because there's nothing else that could be going on. I remember when I first read about him wondering what children were really thinking. And I've never seen anybody do a study on it, but I do know myself that every time I work with these dots, which didn't start when I was 2, every time I work with them, my sense of number becomes stronger. But I also recognize that when I look at a 10, I immediately see a 4 over here, just somewhere. I see 4 dots here, and then I see that I can divide this into 2 3s. I see that. So I suspect that that's actually what's happening with these smaller numbers. But the interesting thing is that it develops so profoundly that you can even get to the difference between 42 and 43, which is unimaginable. I do remember reading research things about, well, you know, crows, they can count to 12, but human beings can only count to 7. No. Crows see lines of crows on lines, or piles of, you know, they see birds in the sky, they see their own flock, and they know how many are there. And they see hunters coming out, and they know whether all the hunters have gone home or one of them has stayed behind. So they are, in a sense, thinking about number. Number is right in front of them, and it's life or death. We don't put number in front of our children and give it a name. But if you put number in front of your child and give it a name, he can get it. And not only that, okay, when you get up to somewhere around 20, you start doing addition. Somewhere around 40, you start doing subtraction, and you do it the same way. You hold up the 23 card with 23 dots, and you say, 23 minus 3 equals 20. And you hold up another card, and you say, 18 minus 7 equals 11. And he sees it, because he can see that thing. Then you come to multiplication, and you do the same thing, you come to division. And by the time he's up at 100, he can walk into a room, according to Glenn Doman, and say there are 273 people in the room. And not that that's a talent we all need. We can survive without it. But what's interesting is it's actually there. The brain is built to use the words that we ourselves, most of us, only use on a sheet of paper after writing numerals on. The closest thing, the most exciting thing I've had happen is over a period of time, probably over a year ago, I did these little videos for my grandson, 1 up to 10, 2 to 11, all the way up to 20. And then, you know, life came in, and that was kind of the end of that. But the next time that I saw him, I had this book. And the book just goes from 1 to 100. It's just very simple. But unlike Glenn Doman is actually using cards. And I actually have a book. So this, I have the numeral 3, I have the word 3, and I have 3 dots. So I sat down beside him, and we went all the way through to 35. And when we were up in the 20s, he was curious what the thing was over here. So I said, this is the word 17, and this is the numeral 17. And his mother had done enough work towards reading with him so that he recognized that this was letters and that this was something else. And he was very interested in that. And then when we came to 23, I said, and this little dash is called a hyphen. And then I turned to the next page and I said 24, and this is the little dash here, it's called a hyphen. So we go to the next page, and I said, this is 25, and he said, and this is the little dash, it's called a hyphen. It's just so funny. And we went all the way up to 35, and then I quit because he just did a little restless thing. Very important when you do something like this, you don't think to yourself, oh, I don't know if you really got it, you know. Let's hold up the 7 card and say, how many is this? No. 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 Children love to learn, but they hate to be tested. And the way you know that they're learning is that their eyes are on what you're doing, and they're paying attention. So I think we did it one more time, and then I went home. But afterwards, my daughter told me that we had just gotten a new abacus. And she said, he wanted me to go through the abacus. So she counted all the way up to 10, to 20, to 30. She said he wanted me to count all the way to 100. Because he was at the point where he understood what all those words meant. And he was curious how it went together. And he just ate it up. It's not a question of testing. It's just a question of how exciting this is. And if we want to raise mathematicians, and maybe that isn't your immediate goal right now, but nevertheless, it has to be a cultural goal. The way you raise a mathematician is you have to have a child who plays with number. Now, I don't remember if I told you the story of Gauss in 2nd grade. I think it was in 2nd grade. Gauss is a very famous mathematician. And when he was early in grade school, his teacher, who obviously wanted a day off, you can just see the whole situation, told all the kids, today I want you to add up all the numbers from 1 to 100. So then she figured she had an hour and a half ahead of her. And Gauss goes, see, Gauss understood number, not just numerals. So he wasn't just sitting there with a pencil, he was thinking, 100, 99 plus 1 is 100, 98 plus 2 is 100, 97 plus 3 is 100, 96 plus 4 is 100. So we're going to get all the way up to 49 plus 51, then we'll have 50 hundreds, and we'll have 50 left. So he said, 5,050. She was very unhappy. Was not her morning plan, but this is what I'm saying. He was seeing number, not just numerals. And at a certain point, a child wants to see the numerals, they want to understand what they mean, of course. And that's why I put them in the book. But number is not the same thing. And when he began to show an interest in the numerals, I told him what they were. But then when I turned the next page, I just said, this is 14, until he asked, because that's what I was doing. And he certainly had the right to do whatever else he wanted. He has the right to that initiative. So it's possible to present the idea of number. Glenn Doman has thought the whole thing through. He had cards and he has a book. Because I'm not that kind of a very tidy person, keeping all the cards in one place and following all of his directions didn't really work in my household. But I did put together a book which anybody else can have who's like me, and you can give it a try. Because even if you don't get all the way through to 100, even if you only get up to 20, the point is that the concept of number is different once you've done something like this. You actually are seeing what number is. And furthermore, every time I do it, my sense of number increases. So it's kind of fun. You know, if you're sitting there on the couch and you're going, this is 23, this is 24, don't be snoring off. Look at it yourself. You can learn too. Nobody is ever too young. New cells in your brain every day if you're paying attention to something that's going on around you. So that's the first thing I wanted to say. After I had built this 1 to 100, I thought, okay, now let me see what else I can do. And so I'm working on a book called Interesting Numbers from 1 to 100. Because what mathematicians think about is number and pattern. Number is interesting because it's a very abstract form of pattern. But the patterns themselves are part of what makes mathematics the key to physics. Because you look into the natural world and you go, wow, that thing just, you know, how can things happen that way? How can things look that way? How can a tree, which puts out its branches just in any old direction, and it ends up being the shape of that kind of tree? And if it's a different kind of tree, it's a different shape. And you feel like, well, the branches are coming out every which way. How do they know? It's really interesting. And it's got names in mathematics for what kind of things are taking place. And when you study the math, then all of a sudden you can imagine that all the DNA has to say is maintain this angle anytime you can. You know, of course, sometimes the wind blows and you can't, or sometimes another branch comes in, or there's another tree nearby. Things happen. But look at the branches, which you can see so beautifully now in the winter, and think about the angle that lies between different branches in each kind of tree. There's a typical angle that sits there. It's really interesting. So what I want to do now is pause for a minute and just talk about the number 19 to give you an idea of what's possible. How many of you have thought about the number 19?
Only since this morning.
Only since this morning. Here's the deal. 19 is a prime number. And what that means is 19 is not part of the multiplication tables. And because it's not part of the multiplication tables, nobody thinks about it. And that's a very small idea of math. And that's the thing that we can change now. For one thing, we have this challenge. On the one hand, we've got this digital thing that is causing people to think of number as punching numerals on a keypad. But the second thing, which in a sense is, has a positive potential, is that we know perfectly well, and the kids know perfectly well, that if you want to know what 42 times 43 is, you can punch it in and you don't need to memorize anything. So either we can skip teaching math entirely, or we can teach something else. So let's talk about 19. First of all, First of all, 19 is a prime number. And in my book, Interesting Numbers from 1 to 100, all prime numbers have these little paths to symbolize the fact that when you have a prime number, you can't divide the number into piles of an equal size. That's what multiplication is. So it has this little path. But then there are some other things that you can do with numbers. If you take an array of things, for example, suppose you take 1 dot, and then underneath put 2 dots, and underneath put 3. Now you have a triangle. This particular kind of triangle is called Pascal's triangle, and a French mathematician named Pascal figured out all kinds of interesting things about it. And the Pascal's triangular numbers are 1, 3, add 3 more, 6, add 4, 10, add 5, 15, add 6, 21, add 7, 28. So it's a progression, and it has an interesting relationship with the Fibonacci series, which some people are teaching because it's fascinating. But there's another kind of triangular number, and this is a triangular number where you begin. I don't know if you can see this. I can tip it a little bit, but you know what? I think. Just stand up and come around if you want to. What you can do is you start in the middle, then you go out in 3 directions to make a triangle, and now the centered triangular numbers are 1, then 4, then you go out again and fill in the sides, and then you add 6 to 4, so that number is 10, and then you go out again, and then you fill in the sides, and you have 19 pieces altogether. So 19 is not a triangular number, but it's a centered triangular number. In addition, you can start in the middle and build a hexagon around it, and then you can go around the hexagon again, and that's a centered hexagonal number. And 19 is also a centered hexagonal number. Now, what's interesting is that's the only time that a number is a centered triangular number and a centered hexagonal number. If there is another number, it's a very big one, because in all of the stuff that I read, I never saw one. And I never did the equations you'd have to do to figure it out. So the point is, here are 2 very interesting designs. Anybody who's interested in design because they knit or crochet or anything else deals with this kind of thing. But here are the numbers. And so So it's just interesting. And it's interesting that 19 would have these two patterns. When you do the Pascal's triangle, 1, 3, 6, 10, you can also do a hexagonal number that just simply starts with 6 like this. 6 in a circle. And then builds outwards. And when you do this kind of hexagonal number, with no center, then it turns out that every other triangular number, not of this kind, every other Pascal's triangular number is also a hexagonal number. But there's no such relationship with these. So it's just interesting what you can discover. And what it does is, when you do these kinds of things, you're inviting your children to play with numbers. And that's what's essential. If you play with numbers, you'll make friends with them. If you don't play with them, you won't make friends with them. Another thing that's interesting, and it's with the number 19 that I bring it up, is 19 is an odd number. It's also a prime number. It's interesting if you lay out the numbers in a grid, just a grid that goes from 1 to 6 and then 7 to 12 and so forth like that. So lay out the grid, and then all the numbers under 2 are multiples of 2, and all the numbers of 4 are also even numbers, and all the numbers under 6 are also even numbers. And all the numbers under 3 are multiples of 3. So, except for 2 and 3 themselves, none of these numbers are prime. Okay? So all the prime numbers are either under the 5 or under the 1. And that's kind of unexpected, that you would have a pattern like that. These numbers aren't all prime, but all the prime numbers are either in this column or in that column. And 19 is one of them. And so then 19 becomes an occasion to talk about some of the things that we can know about primes. One of them is, because all the primes are either here or here, we can talk about twin primes. A twin prime means a prime that has just one number in between. So 11 and 13 are twin primes, 17 and 19 are twin primes, 23 doesn't have a twin because 25 is not prime, and of course 23, let's see, 21 is not prime, okay? 29 and 31 are twin primes. So that's an interesting thing to know about primes. Then there was a mathematician named Ulam, Stanislaus Ulam. He's a Polish mathematician. And he's one of these people who, from the time that he was little, always knew that he wanted to be a mathematician. And he tells about how, when I was 4, he writes in his biography, I remember jumping around on an oriental rug, looking down at its intricate patterns. I remember my father's towering figure standing beside me, and I noticed that he smiled. I felt, he smiles because he thinks I am childish, but I know these are curious patterns. So he knew it right from the beginning. And then when he was 10 years old, I don't think I can find it, yeah. When he was 10 years old, and he was going to school and he had notebooks, he would write on his notebooks, Stan Ulam, astronomer, physicist, mathematician. So sometimes people are it's just there from the beginning. But even if it's not there from the beginning, even if it comes later, and even if you never become a mathematician, you can still become somebody who sees patterns everywhere. It's just such an interesting world that we live in. So those are my interesting mathematicians. My father was also a mathematician. And he had Parkinsonism and came to where it's very difficult for him to carry on a conversation. If he was really concentrated on a conversation, he could carry on a conversation of great intelligence and for a considerable period of time. At the end, he would be exhausted, and if anybody interrupted him while he was speaking, that was the end of it. He couldn't come back to it. That's just part of how that disease works. But he said to me one time when I put him to bed, because he stayed with us for a while, he said, he was talking about math, and he said, math is always there. So he had a relationship with math that was a little bit like what you think a person should have a relationship with Jesus or Mary or something. But when he was by himself and he wasn't able to sleep well, he was always thinking about math. And he could, because he really understood number. As a matter of fact, when he was 6 years old, his grandfather came and lived with the family. And his grandfather had been a school teacher, but besides that, he had learned Italian so that he could read Maria Montessori before she was translated. So basically, my father had a Montessori tutor in the house from the age of 6. Well, I guess that's a pretty big advantage. So, when you are looking for a curriculum, Glenn Doman is actually talking about 2- and 3-year-olds. And I'm saying that I've tried to make materials that are usable at an older age. When you get something like this thing here, which has, something interesting about each number, that's something that you could hand to anybody, but a teenager. And the advantage of it is that this is interesting things about numbers, and this is the next number. So they have a chance to look at these numbers and see number. That's one part of becoming numeral. And then the other part is to see the patterns that go with different numbers. But at some point you may want an actual curriculum. So I just thought I would say, Math UC is a very interesting curriculum that was put together by somebody who taught math on many different levels. And he tells the story of setting out with some high school students and saying, this and this happened, and how many things were left, or whatever. And the kids asked him, do we add, subtract, multiply, or divide? Meaning, I can add, I can subtract, I can multiply, I can divide, but I have no idea what the relationship is between those things and even a very simple problem like putting dominoes in your pocket or something. So he thought, okay, you have to start over here. And then he had a Down's child. And as soon as you have a child with an actual brain developmental problem, you start saying, okay, we really have to see what the concepts are so that they can be presented one at a time. So he put together this curriculum which is very clear and very usable. And it just has concepts in it that I learned. I never really had seen them anywhere else. He's fun. The second thing is Joan Cotter put together a math program called Right Start Math. Joan Cotter was Montessori trained, and she wanted to put Montessori into English and new materials, and also she talked with mathematicians to find out what they think about. And that's when it became clear to her, maybe it already was clear, but anyway, that math is not just about number, it's about pattern. Number is a way of easily talking about patterns, but the pattern consciousness, like a little boy who wants to look at an oriental rug, that's really what makes a mathematician. So be attentive about that. And it's an excellent curriculum. Some people find it difficult because she has concepts that you might not ever have met, and that might be demanding for you. And if it is, either find somebody else who's using it or using Math UC, which is simpler, but it's not quite as wonderful. And the other thing that you can do when children are older is there are really some wonderful biographies. One of the most hilarious ones out there is called The Man Who Loved Only Numbers. It's the story of Paul Erdős. And Paul Erdős was like the St. Francis mathematician. If he won a prize, which he often did because he was incredible, he would give it away to the next young mathematician he met who needed a train ride or a scholarship or whatever they needed. He kept all of his possessions in a couple of brown paper bags, and when he traveled around the country, he turned up at the houses of the people who were his friends and stayed with them until he decided to go somewhere else or something. So his life was completely poor, but he liked to get into a room with 5 mathematicians and say, now I want you to think about this prime number theorem that we've been working on, and then he would start in on you and say, and we've been talking about different problems, have 5 different problems going, like a master chess player playing 5 different chess games. He would have 5 different mathematicians working on different math problems, and as soon as I'd given you your problem, have you figured out anything else about the prime number so we can move forward on it? Hilarious. And the person who wrote the book, Paul Hoffman, is himself a mathematician, but not a St. Francis mathematician. And I just have to tell, this is just so funny. Paul Erdős smoked and drank coffee constantly. And of course, you know, if somebody smokes and drinks coffee constantly, you say, please don't do that, you know, it's not good for your health, blah, 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 you're really addicted. He said, I'm not addicted. So finally, Paul Hoffman persuaded him to give up cigarettes and coffee for a month. And at the end of the month, he said, see, I'm not addicted. But he started right in again. And Paul said, what's that about? He said, progress in mathematics has been set back for 30 days. And he went right back to it. But Paul Hoffman describes, this is very interesting, he describes figuring out a very complicated theorem one time. He'd been working on it for a long time, and you know how you work on something and sometimes you sleep on it? But the answer came to him while he was doing a double backflip. And, I mean, it's just funny, because when you do a double backflip, you run through a process with all of your muscles, and it changes the way things work. Every time you move your hands, you change the way things are working in your mind, and somehow that enabled that last piece to fall into place for him. So a very different kind of mathematician. I don't know whether Paul Erdős ever did a double backflip. He doesn't sound like the double backflipping type. So it's not to say there's only one kind. Another very interesting mathematician, somebody you've heard of, is Kepler. Now, how many of you have ever opened up a pomegranate? And how many of you have ever tried to figure out how those seeds in the pomegranate are arranged? Huh?
It's very interesting.
It is interesting. Well, Kepler worked on it, and he wrote an essay about it. So, I mean, it's just an odd thing. But before the last 100 years, it would just be common that somebody would be able to be thinking about many different kinds of things, astronomy and mathematics and physics. And so Kepler could write about the mathematics of the pomegranate. And that would just be something that would be interesting to him, as it is to me. But it's only recently that I've become so rich that I could get enough pomegranates to think seriously about it. Another thing that's just interesting, I believe Kepler wrote about it, but anyway, a number of people have, is asking the question about the beehive. Now, we know it's pretty clear, even if you take a handful of straws and squeeze them, you start to get a bunch of hexagonal cells. But in a beehive, what you have is a partition, and you have hexagonal cells on this side and hexagonal cells on that side, just 2 sets. And then you have another partition and another set of cells. I used to think that the beehive was solid all the way through, but it's not. It just has a partition and cells. And the cells don't go straight out. They're just slightly inclined, because that helps the honey not to run out. But the question is, what is the shape of the partition between 2 cells in the beehive? And the question is, what is the ideal shape? Clearly, if you had a hexagonal prism with a flat bottom, that wouldn't be the most efficient shape, and besides that, the thing is tipped. So what is the ideal shape? And people have just gone through gyrations trying to figure out, first of all, what mathematically is the most economical way to handle that space, and secondly, whether the bees are using that most economical way, because the truth is that a hive is a little bit irregular, so you can't just open up any old hive and look at it. You gotta think about this. And then thirdly, see, here's the problem. you can solve this problem mathematically, but the wax of which the cells are made has a thickness. And because it has a thickness, edges are a little bit, a little bit rounded. And so the perfect mathematical answer might not be exactly the right answer. But the bottom line is that although I can't remember the names of the geometric shapes because I never heard of them before, the D's have chosen the right shape, oddly enough. So they're good mathematicians. And besides interesting mathematicians, there's an interesting woman named Theone Pappas. She's a mathematician right now, a Greek woman, and she's written all kinds of books on all different levels about math. She's made a calendar with one math problem a day. She's written, I think she wrote a book called Google the Cat to teach the concept of Google. So there's books out there written, and it's important for you as a teacher and as somebody introducing your children to this incredible universe to make sure that in some way your children are engaged with number and pattern and the whole interesting world that's out there, not as a way to pass exams, but as a way to become a richer person. So, those are my thoughts. And if you have any questions, maybe I can answer them, or maybe it's...
I had a question with the dots book. I wondered if part of it was like the photographic memory.
Yes.
Okay, so then the child sees, say 53, and there's this photographic memory of it. Well, you kind of answered the question in that this man can walk into a room and say, this is to some people. But how well do they transfer that to... They do 53 transfer toothpicks, or you know what I'm saying?
And they do transfer it. And one reason for making the book square is so that you can hold it different ways.
Okay.
And diminish that problem.
Sure.
And the second thing is, tempting as it might have been, I didn't take 44 and just add one dot. Mm-hmm. Each page is done separately, and they're all as random as I could make them. Mm-hmm. So
it's beyond that.
It does go beyond that.
So Mary, on the dots then, you tell them what that is. You don't count them or anything, so you just show that and say
absolutely,
there's 53,
you
there's 53.
do not count.
So it's just 50, you tell them that there's 50. Would you start with 1 and you said that this is 1, this is what 2 looks like, this is what 3 looks like.
And it's interesting because when you get to something like 8, your husband or whoever hasn't been listening to my talk, we'll start with your child 1, 2, 3, 4, 5, 6, 7, 8. Okay, he can do that, but remember, this is 1 dot, this is 1 dot, this is... this isn't 2 dots. It's just the second. And the one thing that you can do, because it will make you feel better, I don't know whether your child needs it, is you can get a fast fade marker and draw a line down here. And then say 5 plus 3 is 8. So you can do that. But when you get up to here, this is 34. You can't count that, and your husband can't count it. Nobody you know can count it. No. So this is where you have to face up to something completely different. And once you look at this and think about what it means, then you realize, okay, I need to back up and start from 1. This is 1, this is 2. Because even by the time you come to 10, most people still can't see 10. Yeah, unless they've worked with it.
So how does the random placed dots help with the appreciation or the mathematical part of pattern?
It doesn't help with pattern. That helps just with number, just to isolate the concept of number from everything else. When I wrote this, this here, interesting numbers from 10 to 37, then I have the random number here, because this is just number. And then I have the arrays here, so that you can look at the patterns that come up, the squares that come up, the triangles that come up, the hexagons that come up, the prime numbers that come up, there's all kinds of stuff. There's just all kinds of really interesting stuff. There's, okay, these are pentagonal numbers. Just, and there are also three-dimensional numbers. Think of, 8 is really it's a cubic number, so that's another whole arrangement. And on this page, I teach that 36 is the first number that you can multiply on your fingers. It's very interesting. If you number your fingers, 6, 7, 8, 9, 10, and then you put any two of them together and count 10, 20, 30. The two that you touch and anything below is 10 each, and then you multiply this times this. 3 times 4 is 12. So 3012 is 6 times 7, which is 42. And I remember, okay, this is just totally fascinating to me. I can't tell you why it's true, but I can tell you that I thought about it for a long time trying to figure out why it was true. And one day, when I had seen my spiritual director and forgiven a very old wound that was very deep, it was that day or the next day that I was washing dishes and I suddenly figured out how this thing worked. So, the whole person works in fascinating ways, gets blocked in the most unexpected ways. You're not thinking that mathematics is going to be blocked by childhood memories of stuff. But the feeling that I'm a worthless person can stop you even from doing math. And it's just fascinating. It's just fascinating. Everything is working together.
Hey, Mary.
Yes?
So, I'm the questioner. I'm the
Great.
show the dots. No, I mean the show the kid the dots. So, how many dots, instead of going through first and telling them over and over and over enough that they recognize it. So how long does it generally take the kid to figure it out and then how do you figure out if they really are figuring it out?
And this is where
I like that weird
this
question.
is where humility and self-abnegation come right to the surface. Now we're talking about what does it mean to be a teacher. Mm-hmm. Children love to learn, but they hate to be tested. So you don't say how many. You just keep going. If they're not interested, then you can slow down. Or then you can say, maybe it's time for me to start introducing some addition at the beginning, 3 or 4 questions, okay? So your whole judgment is based on the child's attention. If he's paying attention, he's learning. I promise. God promises. That's it.
How do you figure out how long you have to present it to them? Like how long it takes the kids to
Glenn
actually
Doman
it?
says that you can, that when you're doing this, like 1 to 10, and then you go 1 to 10 3 times a day. What are the chances that I'm going to sit down with my child 3 times a day and do it 3 times? Okay, zip. So, I'm sorry. If I had 2 children, a boy and a girl, 4 years apart, but that isn't what happened. So that gives you a guideline, though, that shows you this is not a half-hour deal. This is just, as long as you're interested. And then I sat down, I said, with my 3-year-old grandson, and he went right up to 35, and he wanted to do it again. And I did it, but I just, I didn't say, oh, gosh, maybe I can get him up to 50. No, that is not the purpose. 35 is plenty, because that's where it was.
So you said don't test them at any point, any age that you actually would present and examine?
Well, you don't need to for this, because this is something that's never going to be on a test. Mm-hmm. So that doesn't matter. But what actually happens in your own life is that all the cousins come over, and all of a sudden there's somebody in the family who knows how many cousins are in the house. And you've forgotten, and you're coming, listen, this family has 4, and this family has 2, and this family has 17, but only one of them, 2 of them don't come. You're going through all of that stuff, and there's one child in the family who says, Mom, it's 35. Whatever. So that's how you know, because things happen. You see stuff. But the point is, you don't need to test for it, and this is true of all fields of learning. A person who is interested is learning. And to interrupt any learning experience to satisfy your curiosity about whether learning is taking place is wrong. So it's just fascinating. It's just a whole task of thinking about stuff. And over time you become more confident. But for just this, that's the thing that you see. That's all.
I like shapes that you brought. What were you looking to say?
This is a rhombic dodecahedron, and this one of these would be a cuboctahedron, and the rhombic dodecahedron has 12 sides and 14 vertices, and this has 14 sides and 12 vertices. And so it's just another piece when you come to the numbers 12 and 14 to say, here are some other things to look at, which have to do with math. They're geometry rather than pattern, but it's just that you're now in 3 dimensions. And the truth is, there aren't really a lot of forms that pack and completely fill space. Cubes do. Obviously, spheres don't. But these two things do. Actually, the cuboctahedron is the crystalline shape at the base of the garnet. So, remember when you grow a mineral, you're repeating something. So it's just interesting to see how that's done. So it's just another way of talking about number and seeing something. There are also tetrahedral numbers. That is to say, if you made an array of triangular numbers, the first triangular number is 1, then 3, and so forth like that, then you build a tetrahedron. Or you can take the square numbers and build a pyramid. And then you have square pyramidal numbers. So it's just another way of thinking about pattern in relationship to number.
Where did you find the patterns, or did you make these?
I made these. You can find patterns online. It's called a net. The net is what kind of paper cutting thing you'd have to do to have a single sheet of paper, a few sheets of paper that you can cut out the squares and triangles, not all separately, but so that you can fold it all up. Sometimes somebody will be clever enough to have just a single net. Like you've probably often seen the net where you have 1, 2, 3, 4 boxes, and then one on each side, and you can fold it all up into a cube. Okay, that would be a net for a cube, but then there are nets for other things. And again, that's a different kind of exercise in math because it's topology, being able to imagine how things are in 3D. Right away, because we've done it, we can all see that cross form folds into a cube. But then to look at something that would fold into this is a whole different thing. And that's interesting. And in fact, the shape that I have had to use for some of the things that I've folded out, which I didn't bring, is it has parts on the inside which are there for stability, and that's another whole engineering point. That there's one net that you need just to be on the outside, but if you're using a light paper, then you need some other things to make sure that the thing doesn't break down the minute you drop it on the floor or bump it.